Welcome to the lab practical for computational chemistry for experimentalists module 6, where we're going to be talking about using different levels of theory to model electronic structure. And we're going to talk about basis sets, we're going to talk about treatments of electron-electron interactions and electron correlation, and we're going to talk about density functional theory and heats of formation. Now, I've logged on remotely to a remote desktop. I've set up my environment variables for Gaussian, and I've moved my current directory to the Windows desktop on here, so I can start running calculations. Now, for this lab, a lot of what we do is going to be using very, very simple molecules, so it's going to be easier to run the results just looking at text input files and text output files, so we're not going to use Gauss view a lot this time. Now, the first thing that I'm going to do, now that I'm on the desktop, is I'm going to open a new file. And I'm going to call this h.gjf, and I'm going to save it on my desktop. I'm going to turn off the remote audio so I don't have to hear that each time I do a thing. I'm going to modify this in Notepad. And I'm going to do the first part of the lab where we look at hydrogen atom using Hartree-Fock theory, which is exact for one-electron systems, if I had a complete basis set, and I'm going to test different basis sets. So I'm going to do Hartree-Fock theory, and I'm going to start with the same 321G basis set that we've been defaulting to all along. So that's my first line, is the method and the basis set that I'm going to use. A comment line, blank line, now my charge and multiplicity. I have 1 spin up electron, I have 0 spin down electrons. My charge is 0, my system's going to be a spin doublet. And it's going to have a single hydrogen atom. And it has some blank lines, and that's all that I need. So I save that. Now I look here. I have h.gjf saved on my desktop. Now I'm going to do run the Gaussian executable with h.gjf as the input and do h.log as the output. I'm not going to worry about the checkpoint file right now. I forgot that I don't need the Unix approach there. So now I'm going to have h.log as my log file. Files. View date modified, desktop, h.log. So here's my output file, and I can scroll down and scroll down and scroll down. Charge 0, multiplicity 2, that's good. Some symmetry information, I'm using the standard basis set of 321G. My calculation runs, it runs and runs, and I get, by the end, some self-consistent field cycles. I get a total energy of minus 0.49619863618 Hartree in this basis set. So I'm going to just illustrate for you the way that I would set this up. You can set up your results any way that you want to, but I'm going to show you how I'm going to set it up. This is one of those places where keeping track of things in a spreadsheet is going to be very useful. So part 1, total energy and polarizability, which I forgot about and we'll show in just a minute, of H atom in different basis sets. So we're going to have basis set, total energy, and polarizability. And we should also put N. I'm going to tell you what N is in a minute. So we're going to do 321G. The total energy, that minus 0.496. 0.6. Polarizability we'll get to in a minute. And N is how many functions did I use to model the atomic orbitals on hydrogen. So to get that, I look at this number in my Gaussian valve. Number of basis functions. So here I use 2. The polarizability, well, I'm just going to show you two things at once here. I'm going to go back and open my input file again. Now I'm going to use a different basis set. If you want to know what basis sets are programmed into Gaussian, Google on the site Gaussian.com, basis. First hit, basis sets. You get a whole list of all the different kinds of basis sets that you can use. There's the 321G that we were using before. I'm not going to belabor what all of these mean, but the general rule is the longer the name, the more functions. So I'm going to here use a larger basis set. CCPVDZ, and I'm also going to compute a polarizability. For hydrogen atom, both the exact ground state energy and the exact ground state polarizability are numbers that we know we can compute exactly using just fundamental non-relativistic quantum mechanics. Double check how do we get polarizability. Site Gaussian.com polar. Compute the dipole electric field polarizability. So we're just going to put in the keyword polar. Now I'm going to save this file under a different name, H-CCPVTZ. Different name so that I don't have to just keep overwriting things. Now I'm going to run the calculation. I'm going to put in here total energy, number of basis functions, and also, just for argument's sake, I'm going to put how long it takes to run the calculation. Since we're computing total energy and polarizability, I'm going to have to rerun this line, but we do CCPVTZ. Now I'm going to run the calculation. HCCPVTZ, HCCPVTZ.log. Calculation runs. Now I'm going to open the results file. HCCPVTZ.log. Now I'm going to need 4 pieces of information from this file. First is how many basis functions did I have? And basis here is 14, a lot bigger than 2. The total energy is going to be down in the section that says SCF done after my self-consistent field calculations are all finished up. And I get minus 0.499809. More negative than my small basis number. The more basis functions I have, the more I get closer to the variational optimum. And you should be able to see that I converge to one specific number for the total energy, and you should know what that number should be. Next is going to be, what did I get for the polarizability? SCF polarizability, isotropic polarizability is 1.88 cubic Bohr. Again, you'll need to total energy. I can always put in here Hartree, polarizability, and basis, and the job CPU. Way down at the bottom. Job CPU time, 2.0 seconds. 2.0. Now last, just to illustrate this, I'm going to go to a really big basis set. CCPV 5Z as I think that's coded into Gaussian by default. Run that calculation. It does run. It doesn't die, so that is coded in by default, at least for the first row atoms. It takes a little extra time, you can see. And now I open the log file here. CCPV5Z. Okay, what do we have here? Well, my number of basis functions is now 80, which is a lot bigger than 2. My total energy is minus 0.49999. You can see we're starting to converge to a value, and hopefully you can figure out by now for yourself what that exact value of the ground state energy of hydrogen atom should be. Our polarizability, isotropic static polarizability now is a lot larger. And the total time that it took to do the calculation is a lot longer. Now it's 5 seconds. So we're not getting a great estimate of computational times from this. To get computational times, you really need to look at something larger, but this starts to give you the idea. And so you go and you go and you go like this, and you're going to fill in a much longer table than this and make sure that you know the exact value of the total energy and the exact value of the isotropic polarizability in whatever units you're going to be using. Now the second part, and I would put this in a second sheet, part 2, dissociation curve of H2 molecule. Now, a dissociation curve is a binding energy relative to bond length. So here, our different rows are going to be different bond lengths, and our different columns are going to be different methods. So the bond length, angstrom. Then we're going to start with total energies, and we're going to replace those with dissociation energies, and we're going to talk a little bit how to do that. So the first method, I'm going to illustrate is just the HF321G, the default method that we were using before. And I'm going to show just one representative bond length, 0.6 angstrom, which is a little compressed relative to the equilibrium bond length. And you'll want to fill this in with 0.65, 0.7, 0.8, 0.9, blah, 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 blah. Also up here, we're going to put a different line, which I'm going to label as just H atom energy, because different methods give different total energies for hydrogen atom. So if we want to compute a dissociation energy of H2 minus 2 hydrogen atoms, we're going to need to know what does our method predict for hydrogen atom. Okay, so here you might want to prepare a new subfolder in whatever directory you're saving all of these in. I'm not going to bother doing that, but you might want to do that. So we're going to say, okay, H atom energy, Hartree-Fock theory 321G. We already did that calculation. H.log, Hartree-Fock theory 321G, hydrogen atom. We got a total energy of minus 0.496. Now, what about H2? Open this file again, and we're going to modify it. We're going to do Hartree-Fock theory. We're going to do 321G basis set we're going to do H2, so our charge is 0. Our spin multiplicity is going to be 1. We're going to look at ground state singlet hydrogen molecule. It's going to have one hydrogen atom, and then it's going to have a second hydrogen atom whose distance from the first one is, in our case, 0.6 angstroms. So now I'm going to save this file. This H2 method, HF321 and 06.gjf. Okay, now I run that calculation. Use Gaussian to run H2, HF631, 6.log. Calculation runs. Open the log file. Okay, here's my log file. I've got 2 atoms. I've got now 4 basis functions, 2 on each atom. Calculation runs. My total energy is minus 1.104. And that's what I put in here. Just to give you a second illustration, and this is going to be useful later, say we do 0.65, 0.7, 0.775, 0.8, 0.85, and I'm going to skip down to 2.0, a bond length 2 angstroms. And I'm going to do this, actually I'm going to do 3 angstroms, I think that's what I need. I'm going to do this for a reason. I'm going to show you something important here. So using the same method, change this to 2.0, rather 3.0. Save it as 3.0, right? Run the Gaussian calculation on this input file. See, I'm not worrying about saving my checkpoint files. I don't really need them here. Open the log file. My bond length is 3 angstroms. I still have 4 basis functions. Skipping down, my total energy is minus 0.802 Hartree. Now, the number that I'm going to plot, so these are the total energies. Over here is going to be the dissociation energies. Remember, the dissociation energy of the bond is the energy of the bond minus the energy of the fragments, and I'm going to do these as kilojoules per mole. The bond length is going to be the same. Control C. This is all going to be the same. But now my energy is going to be conversion factor 2625.5, which is the conversion between Hartree and kilojoules per mole, because I've memorized that, times the energy of the molecule minus the energy of the atoms, which is twice the energy of isolated hydrogen atom. I want to always use the entry in row 3 as the energy of hydrogen atom, but I want to use maybe down here B11 minus 2 times B3. This is an Excel trick. If I put a little $ in front of that number 3, zoom in a little bit here so you can see this a little better. But I put a little $ in front of that B3. So that's my formula, and I can copy and paste this formula. Well, I don't have any values here, so this is just nonsense. I can delete these, but Here my dissociation energy is 295 kilojoules per mole, so at this bond length, H2 is bound by 295 kilojoules per mole at this level of theory. Here, my energy of the molecule is predicted to be above the energy of the atoms, which is obvious rubbish and nonsense and doesn't make any sense. This is a very, very definite limitation of Hartree-Fock theory. This is a limitation of single molecular orbitals. If I use just a single molecular orbital configuration for the stretched bond, my answer is so bad that it's above the energy of the dissociation limit. It doesn't make any sense at all. So you'll see that as you go to coupled cluster theory, you get a much more sensible result. We can talk later about how you can use spin symmetry breaking tricks to get a more sensible result there. You can read some of my papers, some of other people's papers about that, but I'm going to let it go for now. I just wanted to show you that that is important, and when you go and you do coupled cluster CCSD in any basis set, that artifact will go away. One final piece of advice. If I were to do coupled cluster singles and doubles in the 321G basis set, the coupled cluster energy of a system with one electron equals the Hartree-Fock energy of a system with one electron. System with two electrons, it's different. I'll just illustrate this now. So if we take this same system, I'm going to save this as coupled cluster. Instead of Hartree-Fock theory, we're going to do CCSD. Save that. Run this calculation. I should just show you where the energy is going to be. Here's my coupled cluster output file. I go down to the down to the end. I still have 4 basis functions. Coupled cluster theory starts with a mean field Hartree-Fock calculation, so I get an entry that's SCF done RHF. That's the same as I had before, but now I have a bunch of new stuff, and this new stuff all involves the mixing of different MO configurations. So we do an SCF calculation to get what are the MOs, and then we do coupled cluster to get the what are the mixed configurations. There's a perturbative correlation that's done here. Don't have to worry about that. And all the way down this iterative coupled cluster method, This is my total energy, minus 0.993367. So that's my total energy in Hartrees. Copy and paste that. Now I do all of this again. I can copy and paste this whole column. And now you see, okay, when the bond is stretched to 3 angstroms, now my binding energy is negative. It's very, very small, but it's negative. So even at 3 angstroms, when I do a more accurate two-component, two-reference calculation, or correlated calculation, including all the doubles, diagrams, you can read about that yourself. Now I go from being unstable relative to free atoms to very, very, very slightly stable relative to free atoms. So this is the right answer. This is the number that you want. This is the thing that makes more sense. The only problem with doing coupled cluster is when you do things beyond 2 electrons, it starts to get a little bit problematic. It starts to get a little bit challenging. We'll talk later about how to do that. This number, I don't have anything here, so this number doesn't make any sense. I'll just delete that. You can fill all of these in yourself. I also want you to do different basis sets. I want you to try DFT, B3-lib DFT. So that is the end of H2 dissociation curves. I'm going to close this lecture now, and I'm going to go on and do the heats of formation of ethylene. I think we're doing ethylene. I'm going to do that in the second part of this lecture.